All right, guys, it's time for some fun with math today. And what are we doing? So we're going to finish up this lecture on work. So last time we found the work of lifting a rope slash chain, and today we're going to focus on the work of basically pumping out a liquid from a tank. And we're going to use this method of increments again. So remember, to find the work of something, it's just equal to the force times the distance. And the force here, we use Newton's first law, F is always equal to m times A, mass times the acceleration. So let's take a look at the first problem here. And so what we have is a 3-meter deep aquarium that is 4 meters long and 2 meters wide, is full of water. And we want to find the work needed to pump out half of the water. And we're going to use the fact that the density of the water is a constant, 1,000 kilograms per meter cubed. So let's draw our picture here. And so we have a basically a rectangular aquarium here. So let's draw our aquarium. It's 4 meters long and then 2 meters wide. So 2 meters wide and 3 meters deep. And it's full of water, right? So full of water. And we want to find the work needed to pump out half of the water. So find work to pump out half. And so I don't often write down on these problems what I need to find, but today I am. So there's water inside here, and we need to find a small change, we know the equation, a small change in our work, right, to pump out that water. So remember, the work is equal to basically force times distance. And so what we need is to take a small sliver of water in here. So I'm going to take a small sliver of water. So it's just a little sort of rectangular sliver or slice, I guess, here. So there's my slice. If you want to draw it back, you can back here, right? Because I mean there is a three-dimensional aspect to this, right? Because it is a sort of rectangular aquarium back here. So if you want to, you can kind of draw it back, going kind of back and forward and stuff like that if you want. That gives a little bit more dimension to it. And so the idea is here's our x. So we start at the top and go down. And then right here is our delta x. Maybe I'll make that green, make it pop. Right, so right here's our little delta x. And then we can find the force. Right, so remember, how do you find the force? The force is just equal to the mass times the acceleration. And the acceleration here is due to gravity. So we'll take a small change in the mass. That's what this thing is going to be over here. And we'll multiply it by g. And then we'll take it times the distance. And the distance you're going to move this out is just x. And so then what is this going to be equal to? We got to figure out the small change in the mass. And so to find a small change in the mass, we're going to use this density here, delta. And so notice the units on delta is kilograms per meter cubed. So it's going to be delta times small change in the volume. And then we still have this then times our g. So times g times x. And so this is going to be equal to then, I can find my small change in the volume, because my small change in the volume is just the length, which is 4 meters times 2 meters times delta x. So right here, I'll have my delta, which is 1,000, and then times my delta v, which is just 4 times 2 times delta x. And then times my g is going to be 9.8. Right, so g is 9.8 meters per second squared, and then times my x. And so this is going to be equal to, and I can just use a calculator on this since I have a decimal there. So let's just multiply that all out. And so on my calculator, I have 1,000 times 4 times 2, and then times that 9.8. And so I get 78,400 here. So 78,400. And then I have an x and a delta x. Right, so let's make sure I wrote that down right? So I have 1,000 times 4 times 2 times 9.8 And there we go. Okay, so now what can I do? So now I can find the work by integrating from what to what. So I'm going to start up here at basically 0 and integrate down to the height of this thing, which is 3 meters, right? The depth of that. So integral from 0 to 3 of 78,400 times x dx. And I can do that integral. So it's going to be 78,400 and then x squared over 2 from 0 to 3. And so then that's going to equal. And so basically I'm just going to divide this by 2. And I can do that on my calculator, but I think I get 39,200 probably. I should check that, but I'm pretty sure that's right. So let's divide that by 2. Yep, 39,200, and I have x squared from 0 to 3. And so that's equal to 39,200 times, now you plug in your 3, so I plug in 3 and get 3 squared, and then minus plug in your 0, so 0 squared. And so that's just going to equal 9 times 39,200. So again, I'll just do that on a calculator. And so 39,200. Ooh, I can just hit times. Well, sorry. So 39,200 times, and 3 squared is 9. So times 9. And so what does that equal to? And so that's equal to 352,000. I didn't see the last 3 numbers there. And 800. And this is joules. All right, so if we did that right. That should be my answer. Okay, so moving on to the next problem here. Let's check it. Oh, and I should finish this off. So it's picture equation and then solve right here. All right, and let me make sure I hit that on my calculator correct. So 352,800. Good. All right. Let's look at the next problem. So another tank problem, but this time, what are we going to do? Instead of a rectangular tank, we're going to take a circular tank, basically. So we have a circular swimming pool here. It's 2 meters deep. It has a diameter of 6 meters, and it has 1.5 meters in it. We want to figure out how much work is required to pump out all the water. And there's our density, again, of water is going to be given to us. So let's draw our picture. So you circular pool. There's my circular pool. It's 2 meters deep, so it's 2 meters is the height of the pool. It has a 6 meter diameter, so if it has a 6 meter diameter, it means its radius is 3 meters. It's half of the diameter. And there's 1.5 meters of water in it. So right here's my water, and there's 1.5 meters in there. Okay, and then what do we need to find? We're going to find how much water. So how much work? So find, let's do it like this. Let's find work, right, to pump out water. Okay, so let's do it. Okay, so for the equation, I want to find a small change in the W. And remember, work is equal to force times distance here. And so to find that force, the force is mass times acceleration. So I'm going to take a small change in the mass and multiply it by g, and then multiply it by some distance. So over here on my picture, what's the idea? The idea is my x is going to go from there to there. And I'm going to take out a little piece here. So let's take out a little piece, sort of slice this thing and take out a little piece. And if you want, you can kind of give it 3 dimensions. That way you can kind of see it. So here's my little delta x. And so I'm going to take this out a distance of x here. And this has that radius of 3 meters. And so I think that's all I need. So here I have my distance, which is times x. And it's going to be equal to my delta m is what? I need to take this density right here. So my density delta, and then multiply it by a small change in the volume. And I know that because of the units. I'm dividing by meters cubed, and then times 9.8, because that's my g, and then times my x. And so then that's going to equal, I have to find my delta V. And so for my delta V, this is a disk basically, and this is 1,000. So I'm going to have 1,000 times, and again, my delta V is just the area of that disk, which is pi times 3 squared. And then I multiply by this delta x, and that gives me the volume. And so times delta x. And I have this times 9.8, and then also times my x. And so what is that going to equal? So it's going to equal, so on my calculator, I'm going to take 1,000 times 3 squared times 9.8, and that's going to give me a number. So I have 1,000 times 3 squared, so times 9 times 9.8. That's going to spit out a number here. So I have 88,200. So 88,200. And then I have this pi left over. So pi x delta x. And so that's my small change in the work. So to find the work, I'm going to integrate this. So I'm going to add up all these little sort of disks. And what am I going to go from? Well, it only has 1.5 meters in it. So I'm going to start here, and 1.5 down right here is just 0.5. We're 0.5 down from 1.5. So I'm going to start this integral at 0.5. That's where the water starts. And then I'm going to go all the way to how deep it is, which is 2. And then I have this 88,200 pi, and then x, and the delta becomes a dx. And so now I integrate it, and so this is going to be equal to, and then 88,200 pi times add 1, divide by it, so x squared divided by 2, from 0.5 to 2, which is going to equal then, I have 44,100 pi, and this is then x squared from, and this is basically 1/2 to 2. And so what is that going to equal? It's going to equal 44,100, and I plug in my 2, so 2 squared, minus, plug in my 1/2, and so 1/2 quantity squared. And I lost a pi here, so don't forget a pi. And so then this is going to equal, and so I have 40, and so we just do this, this is going to be 4 minus 1/4. And so it's going to be 44,100, and then pi, and then get a common denominator here. So that's going to be, what, multiply top and bottom by 4. And so it's 16 minus 1, which is 15 over 4, which is going to reduce a little bit because these are both even. So what is that? That's 22,050. It must go, oh, it must be divisible by 4 too. That's nice. Okay, so let's just use a calculator real fast. All right, so they can divide that pretty fast with a calculator. And so 44,100 divided by 4 is a nice number. And I'll multiply that by 15. And I can give you the exact answer, which would be 165,375. So 165,375 times pi joules here. And so that's my exact answer. And I don't need to give an approximation, I guess. If you want to give an approximation, you can multiply that thing by pi if you want to. And let's make that 3 a little bit better. So it's 3 right there. All right. So that's the work to pump out that water. Let's zoom out a little bit so you can kind of see the overall problem. And again, there's picture equation, and now I'm solving. And so hopefully you can see it's like all these problems are basically the same, and it's even the same setup, right? So if I come back here, you can kind of look and say, oh yeah, it's really the same thing. And I always do the same thing every time. And as soon as I get started, it kind of just walks me through it. As long as I know work is equal to force times distance, it just kind of slowly walks me through the problem every single time. Okay, what's next? We have one last problem to do. All right, so example 6, another problem, finding the work with tanks. And so we want to find the work required to pump out all of the water if the tank is below is full. We're going to use a calculator then to evaluate the integral. And of course, it gives us the density of water again, because I don't expect you to memorize that. So here's our picture. And we want to find the work to pump out all the water. All water. And so this thing is full, basically. And so how are we going to do that? Well, my little equation is just little small change in work is equal to, well, remember work is equal to force times distance. And the force is the mass times acceleration. So here we're going to take a small change in the mass and multiply by g, and then multiply by some distance. So what's that distance going to be? Well, let's take a small little sliver here. Let's take one little piece, and you can just draw it in one dimension if you want to. Right, so one little piece here, and then just give it a little rectangle. So that's our small little sliver that we're going to take out. And for our x, there's a couple of ways to define x. You can define x from the top right here and go down, or you can define x from the top right here and go down. It turns out it's a little bit better if you do it from right here. And so this will be our distance x, which means that'll be our little delta x. And you'll see why in a minute, why it's better to do that. So let's make this delta x better. So that's our delta x right there. And so to find a little small change in the mass, then my distance, okay, is times x. Because I'm x, here to be careful. It's not x, it's x plus this extra distance of 2. So my distance is x plus 2. So that changes a little bit because I have to take it out of this little top piece right here. And so now this is going to be equal to, so my delta m is like my density times a small change in the volume, right? So that m cubed there. And then you can just plug in 1,000 for this right away if you want to. And then times my g is 9.8, and then times my x plus 2. And so that's going to equal, well, we plug in 1,000 right here, we're going to get 9,800. And then what's my delta v? So my delta v is this length right here, which I actually don't know. So it's just some length. I do know this width right here, it's 8, and then times my little delta x. My little delta x is the same back there. And so this is going to be equal to 9,800 times this length, which again, I don't know. I got to figure that one out. And then times 8, and then times my delta x, and then times my x plus 2. And then to figure out what L is, the easiest way to do this is just kind of blow this piece up a little bit. And so I'm going to redraw that triangle right there, just blow it up a little bit. And I'll draw my L right here. So there's my L. And of course, this distance right here is my X. And then I'm going to draw this all the way down. And so if you look at that, and you know a few things about this, right? I know this distance right here is 3 meters, because that's 3 meters across. And so what I'm going to do here is use something called similar triangles, right? So I'm going to use the law of similar triangles. Because I have a couple similar triangles right here. And so I basically have this sort of little triangle right here, where this distance is L over 2. And then this distance right here, it's kind of hard to see, but remember the height of this thing is 3 meters. It tells you that right here. And so this distance right here is actually 3 minus x. So that distance right there is 3 minus x. And so what do I know? I know that that yellow triangle, if you take L over 2 and then divide it by 3 minus x, that's going to be the same thing as this bigger triangle here. It's similar, but it's going to be this distance here, which is 3 over 2. So 3 over 2. And then divided by this total height right here, which is 3. And so what does that mean? Well, I can move this over to the other side by multiplying it. So I get L over 2 is equal to 3 over 2, all divided by 3, times 3 minus x. And then I can multiply this by the reciprocal 1/3. And so this gives me what? This tells me L over 2 is equal to 3 halves times 1/3 times 3 minus x. And so the 3's are going to cancel. And I move that 2 over by multiplying both sides. So L is going to equal 2 times 1/2 3 minus x. So that's nice because the 2's are going to cancel. And so L is just equal to this 3 minus x. So that was pretty nice. And so there's L for us. And so it's an equal. And so I'm going to have 9,800 times 8. So I'll use my calculator on that. So 9,800, and I'll multiply it by 8. And I get what? I get 78,000. So 78,000, is that 400? 78,400. And then I have my L, which is this 3 minus x, and then times my x plus 2, and then I have my delta x. Good. All right, so now I can find the work. So the work is going to be equal to the integral, and my x starts here at 0, and it goes all the way down because it's full, so down to 3 meters. That's the depth down here is all the way down here at the bottom would be 3. So it starts at 0 up here and then goes down to 3. So I'm going to go from 0 to 3 of 78,400, 3 minus x times x plus 2, and then a delta x becomes a dx. And then if I wanted to, I could integrate this out by hand. I would just multiply everything out, add 1 to the exponent, divide by. But this is kind of a nice problem. It speeds things up a little bit because, let me zoom out here, it's just asking us to find this with a calculator. So let's use our calculator to do this. And so this is going to be basically equal to, and so on my calculator, the fastest way to do an integral is probably what? To hit second, or just hit math, sorry, just math, and then find finite integral. So if you go down, you'll find this FNINT integral. And if you have a newer version of a calculator, it's going to be nice and easy because you just fill in your limits of integration. So 0 up to 3, and then hit over, and I type in 7, 8, 4, 0, 0, left parenthesis, 3 minus x, in parenthesis, left parenthesis, x plus 2, in parenthesis, then hit over, and then for the d blank, we put an x in there, and then just hit enter, and it'll spit out the answer. And so this is actually 1,058,000, and it should be 400 joules. All right, so let's check that on the calculator there. So 1,058,400 joules there. So that looks good. All right, so that's a nice little calculator problem. And so pay attention to the wording of the problems because, sometimes, yeah, you have to integrate by hand, which takes a long time. But sometimes you can use a calculator, which you can just get the answer right away. Let's make that 8 a little bit better. Right. Okay, something was bothering me when I was doing these problems because when I was looking at one of the solutions, I was like, one number was off. So let's go back because there's one little mistake I made here. So let's go back over here to the first example and let's fix this. So what did I find? I found here from 0 to 3 on this first example. So that was to pump out all of the water, but I was only supposed to pump out half. So maybe you caught that, which is good. So I need to change this problem just a little bit. So what is the work to pump out half? So instead of going from 0 to 3, what are you going to go from, right? You still go from 0, but you're only going to go halfway down. So halfway down would be to 1.5 basically. So I need to change this right here. So let's just erase this little number right here and right here. I'm going to replace that with 1.5, guys. So let's correct that in your notes. And so, of course, that's going to change our answer a little bit. So we'll erase that. And so now we'll plug in 1.5 here. And that does half, because half of 3, the total height is 3 here. So half is 1.5. And so that's really what, 3 halves? And so we're going to plug in 3 halves. And so here I'm going to square, and then put 3 halves here. And so I'm going to square this 3 halves and get 9 fourths. And then you can just use a calculator on this one. And so here we have 39,200 and then times 9 divided by 4. And now I get this 88,200, which is the right answer, right? So 88,200. So make that change in your notes. And, the reason why I write down what you need to find is to try to remind myself, did I do the right thing or am I just going through the motions, right? So it doesn't always work, but if you write it down, you can kind of check your work at the very end and make sure, hey, did I find that? Did I find half because sometimes when you do these problems, you're like a machine after you get kind of used to them. All right, so that's all I have for you guys today. Take care.